So today we are going to focus on the standard exact flat workflow. We are going to examine each aspect of the workflow and discuss it in detail. And we are ultimately going to apply that workflow to this chair here. And I will show you how we can take this 3D model of a chair and produce a 2D flat pattern and a drawing document for this particular chair. So we're going to start with the exact flat piece creator. Once this is open, we have our main input box, and this is where we can start adding faces. So as we look at this chair here, we've got multiple faces color-coded in yellow for the backrest. We've got a couple in magenta for the seat, and the sides of the chair also have multiple colored faces. So each color represents our ideal piece of fabric to use as a pattern piece. So with the piece creator, what we can do is we can just simply start selecting faces here, and this will allow us to effectively knit these together. So internally, we're just using the SOLIDWORKS knit surface feature to knit all of these faces together. As we start picking faces, we're going to notice there is a red arrow emanating from the pattern pieces. This red arrow indicates the facing up direction of your pattern piece. So if this fabric were to be laying down on a cutting table, this red arrow would be pointing up towards the ceiling. Because this is the finished side of the pattern piece here, this is the side that we actually want facing up towards the ceiling. So all we do is we just click on the red arrow, and that will flip the orientation of the pattern piece. Once you have your faces selected, you can click the Create Piece button, and this will create your pattern piece. So now down here in the Piece Manager, we have a new piece. Piece number 1 has been added to the Piece Manager. We can continue carrying on, selecting additional faces, and as I select additional faces, once again, we have that red arrow emanating from the piece. And again, this is in the wrong direction. So we're just going to click on the arrow, and that will flip the orientation of the pattern piece. If you're noticing that every single pattern piece is being created with an incorrect orientation, you can change the default piece orientation option up here from normal to flipped, and that will automatically flip every single piece orientation as you start creating the pattern piece. So we have our 2 faces selected, so we will go ahead and click the Create Piece button here to create a new piece in the Piece Manager. You can also use the Enter key on your keyboard to quickly add pieces to the Piece Manager. So once you've selected all your pieces, you can just press Enter, and that will very quickly do the same thing as clicking the Create Pieces button. As we add our pieces, we will also notice that the pieces are automatically being named for us. They're being named in sequential numbers. This name is being generated from the exact flat options. You have quite a bit of control over how your pieces are being named, so you can change the template and the format of this name to include things such as file name or the body name, or even SOLIDWORKS custom properties. And we will look at that in a bit more detail tomorrow when we talk about the exact flat options and the exact flat database manager. If we want to change this name at any time, we can do so either after the piece has been created or while the piece is being created. So for this piece here, if we wanted to give it a more meaningful name, we can simply change the name to whatever we want. So for this piece here, I'm going to call it Inside Right. And because we haven't actually created it yet, we'll go ahead, we'll press Enter on our keyboard to create the piece. We'll go back to these 2 pieces here, and we'll rename these pieces so they're a little more meaningful. So we just select the piece in the Piece Manager, we bring our cursor up here, and we change the name of the piece. And we'll do the same thing for this one. And we'll finish creating our pieces here. Once your pieces have been created, we can click the green check mark here, and that will close the PMP and insert the piece creator feature into the feature tree. This is a good point in the workflow to examine your model. You want to make sure that there aren't any holes or gaps, and if we look in the feature tree here, specifically the surface body folder, we can see the results of the knit surface feature. Every single piece has now been created as a separate surface body. So we can select each surface body one at a time, and we can just rotate around to make sure that we don't have any extra faces included in our surface body, and to make sure that there aren't any holes or gaps in the surface body. So it looks like our selections are all good. If we did notice an issue with the piece selection, we can always go back to the Create Pieces button. We can open up the Piece Creator again, and we have full access to our pattern pieces. So if, for instance, we realize that we no longer need the seat here, we can simply select the seat from the Piece Manager, and we can dissolve that part, and that effectively removes it from the Piece Creator. If we realize that we forgot to add a part, or if we forgot to include a face in a part, we can simply select that part. So for now, we'll add the seat pieces to the inside pieces. So we can select a piece here, we can edit that piece, and now we can either remove the undesired face by holding Control and clicking on it, or we can add additional faces by simply selecting them. Once we've made our change, click the Update Piece button to save changes. We don't actually want to join these two pieces together though, so I'm going to once again edit my piece, and I'm going to remove that face and update my piece. Similarly, if we forgot to add pieces, we can just create a new piece by selecting the faces, give it a name, and click the Create Piece button. We can now close the Piece Creator and accept changes, and all of our pieces are formed. After we have finished with Piece Creator, we can now start the flattening process. The entry point to the flattening process is the Convert to Exact Flat button. Just a reminder, once we click the Convert to Exact Flat button, we will no longer have access to the Piece Creator. We will not be able to modify our pieces or add or remove faces. So make sure that your model is accurate and complete at this point, and then we can move on to Convert to Exact Flat. So once we're happy with our model, click the Convert to Exact Flat button, and this will start the conversion process. The conversion process will first create a mesh from our model for flattening, and lastly we will assign a material to each piece that we have defined with the Piece Creator. Exact Flat is a two-stage flattener, so we do our flattening in two separate steps. The first step is a very fast pre-flattener that is applied to the mesh created by SOLIDWORKS. And the second stage is the optimizer, where we use the mechanical properties of the material to relax the curvature and the average energy density of the mesh to as close to zero as possible. The second stage flattening does use the mechanical properties of the material, so that's why we're being asked to pick a material at this point. In addition to setting up the flattener, materials are also used to set up your markers. So each material not only contains a name and description, but it contains the mechanical properties for flattening, as well as the dimensions of the material for nesting. So from the material selection, we can pick, we can assign one single material to every single piece, or if your part is designed with multiple materials, we can pick individual pieces here, and we can assign different materials to different pattern pieces. So you can assign as many materials as you want to your different pattern pieces. The only important thing here is that we do assign a material to every single pattern piece. So for this particular model, we're just going to assign laminate for car seats to every single piece here, and we will go ahead and click OK. After the conversion process, we have our chair, and we can see that the color has changed to pink. So pink is the color associated with the material we selected. If we had selected multiple materials, then we would have seen multiple colors on the car seat, and each pattern piece is color-coded for the specific material that was selected for it. Once the conversion process is done, we now have access to the flattener and the View Patterns buttons. So now we're going to click View Patterns, and this is going to bring us to our 2D flat patterns. From here, we can see the initial unoptimized 2D flat patterns. As I mentioned previously, ExactFlat is a two-stage flattener, so the results we are looking at are simply the results of one of our pre-flatteners. We haven't finished the flattening process. We still need to optimize the shape of our pattern pieces. To do this, we are going to open up the ExactFlat flattener. And once open, we have access to all of ExactFlat's flattening controls. The flattening interface is divided into three main areas. At the top, we have our model and pattern viewports. The controls in the viewports are exactly the same as in SOLIDWORKS. So we can orbit around our model by holding middle mouse button and dragging our mouse. We can zoom in and out by holding Shift and using our mouse up and down. And we can pan around by holding Control and pressing middle mouse button to pan around our object. The controls are exactly the same in the pattern viewport, with the only difference being we can't orbit around our objects. The pattern viewport is locked to an orthographic projection, but we can still zoom in and out, and we can still pan our camera. Below the viewports, we have our toolbar. On the left, we have our flattening controls, and on the right, we have our highlights, where we can turn on or off different visual cues. And below that, we have our pattern piece list. Whenever we click any of the controls, the flattening controls, that operation is going to be applied to whichever pattern piece is selected down here. So by default, every single pattern piece is selected. However, if we only want to apply an algorithm to a very specific pattern piece, we can single that piece out, or we can select multiple pattern pieces. We do have multiple highlights that can be turned on or off, and the multiple highlights can be used for many different things. Starting with the first highlight here, this is our piece normal. We can use this to show the normal direction of the pattern pieces, and this is functionally equivalent to the arrow that we saw in the piece creator. If we turn this on, we will see little red line or little black lines emanating from the pattern piece, and these emanate and point out towards the facing up direction. So in most cases, you want these lines coming out of your pattern piece. You don't want them going towards the inside. If you see those black lines on the inside of the pattern piece, usually it means your face normal has been reversed, in which case you're going to have to undo the flattening process and then fix your piece orientation in the flattening window. The second option here will turn off flat shading, so it will introduce lighting into our document. In most cases, it just makes our model look gray, so it's not a very useful option, so we're going to turn this off. Our third option will turn on or off the edge triangulation, and this is useful if we are trying to examine the strain of the model. It's often easier to examine the strain of the model without the triangulation visible. We can also use the edge highlight. We can turn it off to make it easier to spot folds and wrinkles in our pattern. So if we look at this piece over here, this would be a good example of a pattern piece with folds and wrinkles. Whenever we see these green crosses and inset triangles, that's an indication that we have a fold or a wrinkle in our pattern piece. The fourth option is the wrinkle highlight. We don't ever recommend that you turn this off. If you turn it off, it simply hides the folds or wrinkles. But because folds and wrinkles are considered to be patterning errors, it is not recommended to turn that off. The last option here is the strain map. If we turn this off, we no longer see the strain map on the pattern piece, but it's very useful to turn that off if you're looking for folds and wrinkles. They're very obvious on this piece here, but if our pattern only had one small fold or wrinkle, then turning off the edge highlight, turning off the strain map will make it very easy to pick that out and spot the fold or wrinkle. So we are going to turn back on the strain map, and we are going to turn on our edge highlight. Moving on to the flattening controls. Our first group of buttons here are our pre-flatteners. Starting from left to right, we have our Smart Fracture pre-flattener. We have our Fracture pre-flattener. We have Stretch Initial. We have Stretch Minimal or De-Wrinkle. And we have Stretch Round. And lastly, we have Pelt. The pre-flatteners are simply 2D algorithms used to take the 3D shape of the mesh and generate any kind of 2D flat pattern. The flat pattern created by the pre-flatteners is not an optimized flat pattern. However, they are very fast and they're used to generate A, a 2D flat pattern, and B, hopefully a flat pattern that doesn't have any folds or wrinkles. We have many different algorithms because the different algorithms work better on certain types of geometry. And because of the nature of folds and wrinkles, if one algorithm produces a fold or wrinkle, you can then try a different algorithm to try and produce another flat pattern that doesn't have any folds or wrinkles. Starting with fracture, every time you click the fracture button, we will generate a new unique flat pattern. So we're going to isolate on the backrest here, and we'll look at the effects of the pre-flatteners on this particular part here. Every time I click the fracture button, we're going to see a new unique 2D flat pattern being generated. In this case, we've got fairly low strain spread out through the part, and we don't see any folds or wrinkles. The starting point for fracture is always randomized, and as we fracture a part, we're actually pushing the material outwards from the starting point. So every time I press this button here, we are randomly picking a new starting edge, and we're going to be pushing the material outwards from that starting point. Fracture is very similar to this. It doesn't have the same built-in intelligence that Smart Fracture does, so it tends to produce patterns that have more folds and wrinkles, whereas Smart Fracture, when it detects a fold or wrinkle, it will attempt to correct that and then finish its algorithm. Our stretch initial algorithm works very well on pattern pieces that are comprised of 1,000 vertices or fewer. However, once we have more than 1,000 vertices, the results become unpredictable, and we typically start to see this type of result here. De-wrinkle works very well when we have a pattern piece with a shape that is very ideal, such as this, but we have a few folds or wrinkles in it. It is similar to the stretch initial, so just like stretch initial, it works really well on pattern pieces under 1,000 vertices. But once we have more than 1,000 vertices, the results become unpredictable. So we'll try de-wrinkle on this piece here. And in this case, it removed most of the folds or wrinkles, but it still produced this spike down here, which is not ideal. Our round algorithm does exactly what it sounds. For this one, we will move to one of the side pieces here. They have fewer vertices. So this basically turns your pattern piece into a disc. It's not very useful for this type of shape. However, if we were flattening something like a dome, then this algorithm would become very useful. If all else fails, if every single algorithm fails to produce a pattern free of folds and wrinkles, then round can be used. It might take a little bit longer to optimize, but the important thing is that we don't have any folds or wrinkles when we start the optimization process. So round can be used to get a pattern if no other algorithm is going to succeed. Moving back to our backrest, our last algorithm is PELT. And this algorithm tends to produce patterns that have moderate strain, but it is almost always guaranteed. So fracture and Smart Fracture, they tend to reduce or give patterns that have the least amount of strain, but they tend to only work on developable surfaces. As you move away from a developable surface, the chance of success with Fracture and Smart Fracture starts to fall. CCM, or stretch initial, de-wrinkle, and round, they only work really well on low vertex count pattern pieces. As soon as you get more than 1,000 vertices, they tend to fail. And then the last one is PELT, which tends to work well on all pattern pieces. However, it tends to produce more strain. So strain is calculated for every single pattern piece, and as we look at our pattern piece here, we can see different colors on it. If we look at our model as a whole, we can see a rainbow of different colors, and we actually use the color to represent strain and sag on the pattern pieces. As we look at our pieces here, we can see we have white, cyan, green, yellow, and red, and we use white to indicate no strain or sag on the pattern piece. So if we had the perfect pattern we would expect to see the entire surface area of the pattern as white. As we move through the spectrum, cyan represents up to 10% strain, so, up to 5% strain. Green is up to 10%, yellow is up to 15%, and red is 20% or more. So this allows us to just very quickly glance at our pattern, and we can just visually tell how much strain is on that pattern. To put this into perspective, strain can best be thought of as how much you're going to have to stretch your material to get it to fit the original shape. So if we look at this piece over here, we have a lot of red on the pattern piece, and that's telling me that the surface area of this section of the piece is much smaller than the actual 3D model. The surface area of the 2D pattern piece is much smaller than the surface area of the 3D model. So if we were to cut this pattern piece out and try and fit it to the chair here, we'd be stretching our material 20% or more to get it to fit, and ultimately we'd probably tear the material. So we can use the strain map to very quickly tell us how accurate our pattern is, what the quality of the pattern is. Similarly, the seat pattern right here, it's pretty much all white. So if we were to cut this out, visually this tells me that we'd have pretty much a perfect fit here. We wouldn't have to stretch our material to get it to fit. It would be a very natural fit. So with all this in mind, our goal is to eventually optimize our pattern pieces to give us our final optimized shapes. In order to do this, we first need to use a pre-flattener to generate some kind of 2D flat pattern, and this is in most cases done automatically for you during the conversion process. However, if you have folds and wrinkles here, these do need to be fixed before we can optimize. So in the case of these pieces here, we need to remove the folds and wrinkles before we can optimize. And the way we do that is just with a different pre-flattener. So this piece here, we can try our Smart Fracture. This piece is fairly close to developable surface. So Smart Fracture gave us a pretty nice looking result here. We can see from the colors of it that we have fairly low strain all throughout the pattern piece. We're seeing mostly white. We do see a bit of color in these areas here, but overall, this is a very good looking pattern. So we can stick to this pattern here. We'll do the same thing for the outside left. Again, we have folds or wrinkles here identified by the green check marks. So we are going to try a different pre-flattener. We will try Smart Fracture. And again, we've removed the folds and wrinkles. We've lowered the strain on the pattern piece. So this is a good starting point. As we look at our whole model as a whole, we don't have a lot of pattern pieces. Our seat is still a circle. So we'll focus on the seat and we will do Smart Fracture to that. And now we have a much nicer looking pattern there. So in terms of optimization, this would be a good starting point for optimization. We've used the pre-flatteners to generate a 2D pattern, and we've used them to remove the folds and wrinkles from the pattern piece. Additionally, as we use the pre-flatteners, we also reduced the amount of strain in the pattern pieces, which is ideal for optimization. So our three main goals for the pre-flatteners are, first and foremost, we want them to generate a 2D pattern for us. Second, we want to use them to remove folds and wrinkles from the pattern pieces. And third, we want to use them to reduce the strain as much as possible before optimizing the pattern piece. The performance of the optimizers, our second stage flattener, is dependent on a couple different things. First of all, it's dependent on the number of triangles or vertices that are being optimized in the mesh. And second, it's dependent on the amount of strain in the mesh that has to be resolved. So this ties back into our pre-flatteners. As we pre-flattened our side pieces here, the color went from red to pretty much white. So if we had optimized them as pure red, that's 20% or more strain, it would have taken longer to optimize than what we have now with them being pure white. So the more strain you can remove with a pre-flattener, the better. So in a typical workflow, you would open up your flattener window here. We would do one of our uniform remeshers. We're going to look at that next, and that would reduce the triangle and the vertex count of your mesh. And then you would use a pre-flattener to both remove any folds or wrinkles that may be in your mesh, but also to reduce the strain, because the pre-flatteners are so fast, we can use them to reduce the strain. And then we can ultimately optimize the pattern pieces. So moving on from our pre-flatteners, Our next grouping of tools over here, actually this icon right here is our material editor. So if during the conversion process you accidentally click the cancel button or you forgot to assign a material to a pattern piece, you can do that in two different ways, and we'll look at another way after we're finished with the flattener window here. But if you forgot to assign a material to your pattern piece, you can click this button here. This will open up the material selection interface and allow you to assign a material to your pattern piece. As I mentioned previously, the materials do contain the mechanical properties of your fabric. So you do need to assign a material to your pattern piece in order to be able to optimize your pattern piece. You will not be able to optimize your pattern pieces. That is the second stage flattener. You will not be able to do that until you assign a material to your pattern piece. So our next grouping of icons here are our remeshers. We have our uniform remesher and our adaptive remesher. These two tools have the exact same goal. They are used to analyze the curvature and the 3D shape of a mesh and produce a new mesh over top of the original with a lower polygon or vertex count. The two remeshers function slightly different from one another. With the uniform remesher, we typically set a target vertex count and we set some fidelity constraints, and these are changed. We change these in the exact flat options, and we'll look at how we change these options tomorrow when we look at the exact flat options. So with this one, we set a target vertex count, and the uniform remesher will remesh to that target count. The adaptive remesher differs in that we simply specify the maximum allowed distances from the old mesh to the new mesh. So we can set the maximum allowed distance in terms of surface to surface. We can set that in terms of boundary to boundary. And we also set the minimum allowed edge length of any triangle edge. And using that information, the adaptive remesher will automatically determine how many triangles to place onto that mesh to both minimize the triangle and the vertex count while maintaining the curvature of the mesh. So in a normal workflow, I would recommend using the adaptive remesher. Typically, when we use the adaptive remesher, it produces a really nice looking mesh. But for this particular seat here, because we have a lot of double curvature on it, specifically around the arms, and due to the complexity of the triangulation, we actually get a better result using the uniform remesher. So for this particular chair, we're going to use the uniform remesher, even though in a normal workflow, we recommend the adaptive remesher. Our next icon is the optimize icon. So when we click this, we will launch the optimization process, and we're going to look at not only the remeshers, but the optimize icon in a moment here once we finish up with our toolbar. But when we click this, we will start the optimization process, and that will relax all the strain on the pattern pieces to as close to zero as possible. We're going to be minimizing the average energy density across the pattern to as close to zero as possible. Our next icon here, if we are running one of the remeshers or the optimizer, this icon will appear, and this will basically halt the optimizer or the adaptive remesher. So if you start in a process and realize that you're not ready for that, so if I accidentally click the optimize button and I realize I'm not ready, I forgot to optimize, I can cancel the optimization and it's not going to do any optimization to the pattern pieces. Our last icon here is the broom icon. And if we do some kind of operation, let's say for this chair here, I know the adaptive remesher isn't the best remesher, so let's say I accidentally click that and I want to undo the effects of the adaptive remesher. I can click the broom icon here, and this will essentially restore the original input mesh that was generated by SOLIDWORKS. So after clicking this, I'm going to see my original mesh being restored. There's a lot of different buttons here. However, in a typical workflow, you don't need to press all of them. So the only time we really need to play with the pre-flattener buttons is if we notice any kind of fold or wrinkle on our pattern, or if we have an extreme amount of strain on it. So if we saw after remeshing or after flattening one of our pieces was red like this, that would be a good use case for using a pre-flattener on that piece. But in a typical workflow, all we do is when we open up the flattener window, we would remesh our model, and then after remeshing, we would optimize the model. So even though we have all these controls here in a typical workflow, we only press 2 buttons. So after opening the flattener window, normally what we do is we just remesh. In this case, I'm going to use the uniform remesher. And as this is running, we can see it's reducing the triangle and the vertex count. And once that's finished, we would then optimize our pattern pieces. So we'll start the optimization process, and very quickly we are going to see ExactFlat take over, and it's slightly changing the shape of our pattern pieces. As the shape is changing, we're going to turn our edge highlight off to make this easier to see. We can also see the strain on the pattern is being relaxed, it's being minimized, and we can tell that it's being relaxed and minimized just by the color of the pattern pieces. So for most pieces, we have mostly white, indicating no strain. We have tiny bits of cyan on our pieces, which tells us that we have up to 5% strain. And in some pieces, we actually have a bit of gray here. So gray represents sag on the pattern pieces. If we see sag, that tells us that we have a bit of excess material, and that may manifest itself on the final sewn product as puckering or fingers of material, just because there's an excess of material in that area. So we can use this to help us make decisions on how to refine our pattern. If this is okay for your pattern, then you don't have to make any change. But if you don't want any sag, let's say we don't want any sag specifically right here, this may be an indication that we might have to split this part into multiple pieces, or we might have to add a dart or a relief cut. And we can do that simply by undoing the flattening process, and we can split our part either in half, or we can split out a small dart of material and then redo the flattening process without that dart of material. So at this point, we have remeshed our part and we have optimized it. So assuming we don't have any folds or wrinkles and our part has been sufficiently optimized, we can then click the OK button, and this is going to update our planar surfaces in the SOLIDWORKS environment with the results of our flattening process. So after flattening, we have our optimized 2D pattern pieces here in the pattern viewport. From here, we can start our patterning process. It's difficult to really tell where these different pattern pieces go and how they sew together. So the first thing we normally recommend is using the Move Pieces tool to arrange our pattern pieces. The tool has a variety of different modes. The first mode is the translation tool, and this tool allows you to simply drag and drop your pattern pieces. So I'm dragging this piece around. We can see the gray highlight of where my pattern piece is going to go, and when I release my mouse button, the piece is moved up there. Internally, this just uses Move Copy Bodies, so you can manually insert your own Move Copy Bodies. However, the Move Pieces tool is a much easier way to just drag and drop your pattern pieces. We also have a rotation tool. So with this tool, when it's active, when I click my mouse button and drag, I'm rotating my pattern piece. And again, we can see that gray preview of where the pattern piece is going to go. So we can rotate this to however much we want, and it will rotate our pattern piece for us. We have two alignment tools. We have our vertical and horizontal alignment tools. And for each one, for horizontal alignment, we can pick either a bottom edge or a top edge. And for vertical alignment, we can pick either a left edge or a right edge. And we can use these to help us align our pattern pieces so they are in the correct orientation. If we look at these two pieces down here, we've got very long straight edges. We know that these are on the backrest, and we know that these edges should be perfectly up and down. So we can use our vertical alignment tool to help us arrange these pattern pieces. For this piece down here, I know this is supposed to be on the left-hand side. So I've got my vertical alignment tool selected. I have left edge selected. And when I click and hold on this piece, we can see it's rotating. So this part, that selection point is perfectly up and down. I'm just going to move this piece up here. And our last tool is our Find tool. This tool is used to find neighboring pattern pieces. We can set an optional offset here. I like to give myself a lot of extra material, so I'm going to change this to 300 millimeters to give myself a lot of space. When I click on an edge, again, I'm going to click and hold. We have our preview on the left-hand side, and we also have a green dot appearing on that edge. So for this particular edge, because my edge is pretty much straight, we're not going to notice a big difference. But as I move my cursor up and down, we can see our gray preview rotating. So the pattern piece is tangent at this green point. We'll notice a bigger difference over here as we start finding this neighboring piece here. So as I move my mouse, it's rotating my pattern piece. So my two pieces are tangent at that same point at a distance of whatever my offset was set. So once we have a desired location set, just release your mouse button and Exact Flat will snap the pattern piece to that location. Find our top piece up there. And then this piece kind of sits down here, but it might be better just to move that up here. So what I'm going to do is I'm going to use my bottom edge alignment tool, rotate that to a bottom edge. I'm just going to translate this piece up here like that. So now that our pieces have been arranged, it becomes pretty clear how this sews together. So we can start adding our seams and hems. If after using the Move Piece tool or any other tool, you notice that your seam and hem tools are not available, just click in the empty white space here and that will reactivate the toolbar for you. Now that we can have access to our seam and hems tool, we will open up the seam tool and we can start to add seams to our pattern piece. It's very important that you think of seams as individual sewing operations. That is, you have to create your seams the way they would actually be sewn together in the assembly process. A lot of the times, people will tend to just rectangle select everything, and if you do that, you will probably succeed in adding your seam allowance to your pattern pieces. However, none of your notches are going to align, and that's simply because you're considering every single edge in your document here as one side of a sewing operation. So you need to consider this as a sewing operation, and when we start selecting our edges, you want to select them in the order that they would be sewn together. So if we zoom in on this part here, we have one really big long edge in the center, but we have a very small tiny edge down here at the bottom and a tiny edge at the top. So we want to make sure we select them in order. So we'll start here at the bottom, we'll select that edge, and as I select that edge, we have a green dot showing the start of that edge, and we have a red dot showing the end of that edge. We can also see the additional material that has been automatically added to our part as part of our seam allowance. If we zoom out, we can see over here on the neighboring pattern piece, we also have the exact same information being shown. So we have our green dot here at the bottom and our red dot at the top. As we start selecting additional edges, we can see that our seam is being expanded, and we'll make sure we pick our final edge. So we can see that Exact Flat automatically recognizes and finds the neighboring edges for us. It's really important that we want to make sure that the seam starts and stops on the exact same side. So we want to make sure that in the case of this particular edge here, both our green dots are at the bottom, and on both sides we're sewing up the pattern piece and stopping at the red dots up here. If for whatever reason one side was reversed and not in the correct orientation, over here in the seam PMP, we can simply click the reverse direction button here to reverse the direction of one of our sides. Scrolling down, we can do additional things to our seams. If, for documentation purposes in SOLIDWORKS drawings, we wanted to add a seam table with more specific information, we can give our edge a name. For the purposes of this demo, though, I'm just going to leave this empty. But if we were to give our edge a name and we did add an edge table, the edge name would appear in that edge table for descriptive purposes. Below that, we have our seam properties. This is where we can adjust the amount of additional material that is being added to our seam. So for this particular file, my default is 1/2 inch pinch. If I wanted to change this to something else, I can do that by just changing my seam type here. If I select 6mm join, we can see material has been removed from our seam allowance on both right and left hand side. And as I pick additional seams here, we can see the amount of material is being changed depending on my type of seam. We will look at the end conditions of the seam as we start adding additional seams. It will become a little more clear what the different end conditions do. So we're going to skip the end conditions for this seam here, and we will look at this with our next seam that we create. Scrolling down, we now have our notch chain properties. So if we wanted to apply a chain of notches to this edge, we can do that by simply turning on the notch chain. When we turn it on, we're immediately asked to select a notch type. I will pick our 1/4 inch V notch. And very quickly, we will see an array of notches appear on our edge. We can control the number of notches that appear by simply changing the number of notches on our edge. So if I change this to 9, we now have 9 notches arrayed along that edge. If we want to, instead of specifying the number of notches, if we want to specify the distance between notches, we can do that by changing our mode from count to spacing. And now we can place notches at whatever interval we want. So right now it's 100 millimeters. If I change this to 200 millimeters, then the distance increases. So we can change the way we create our notches either by specifying a notch count or by specifying the distance between notches. So once you've finished adding your notch and setting your end conditions, your notch chain, we can then go ahead and click OK, and this will finish adding the seam for that particular notch. In most cases, after you've finished modifying or creating a new seam, your edges will still be selected, and the implications here are if we go to open up the seam PMP again, if you already have an edge selected when you open up the seam PMP, your seam PMP will be opened up in edit mode. So you will be editing the seam that you just created. If you notice that you already have a seam there, just go ahead and click the red X. That will close the PMP. And then click in the white space to deselect your edge. This will deselect the edge and allow you to create a new seam. Another option is to pre-select your edges first, and this guarantees that you won't be opening up your seam PMP in create mode. So if you pre-select your edges first, this will eliminate the chances of opening up the PMP in edit mode. So we're going to add the next length of seam down this side here. So we select our top edges up here, open up the seam PMP, and ExactFlat will automatically detect our neighboring edges for us. ExactFlat remembers the last settings used, so because we already configured our previous seam to be a 10 millimeter join with a notch chain with 9 counts, ExactFlat automatically applies those settings to every single seam created afterwards. So the previous seam settings will always be applied to the next seam. We're going to have a look at end conditions and how they work. And these are applied to the ends of a seam. So on this particular seam here, we can see we have our green dot there, and we have 2 seams coming together. So the default end condition for most of our seams is trim extend, and what that does is instead of having our seam simply extending from the edge, it's going to extend our seam line and trim it at the intersection point of where the 2 seams meet. We can change the default end conditions by turning off use default end conditions, and this gives us access to all of our different end condition types. Trim extend is the default. Our other types are chamfer angle and chamfer to corner angle. So if I change this edge to chamfer angle, we can see that we are no longer trimming or extending the edge and trimming it. So the angle is always going to be a deflection angle from the perpendicular direction of the edge at that point. So 0 is no deflection, so we have basically a mitered edge here. If I change this to, for instance, 45 degrees, we're going to notice that edge is now being rotated 45 degrees inwards. So you can change your chamfer angle to whatever you want. This is very useful for hiding excess information or excess material, so you don't have a large amount of material balling or bunching up at your corner of your seam. Chamfer to corner angle is very similar. This option simply attempts to mimic the intersection angle over here. So you have a very smooth, flat seam. So it doesn't show very well on a 90-degree corner, but with other seam types, you'll notice that it's going to be trimmed to the same angle as the intersection, just so when you fold that down, you're not having excess material sticking out. So for this particular seam, I'm going to leave it at our default of trim extend, and we will move on. So we can carry on adding seams to the remainder of the part. And in most cases, because ExactFlat automatically applies the last settings used, all you have to do is select your edges, open up the seam PMP, and then you can click the OK button, and ExactFlat will create your seam for you. For our last few seams down here, this is where parts of our cushion sew together. So we will create our seam along the front here. And in this case, we can see our seam is actually jumping from one piece to the next. So that's telling us that even though we have one continuous piece of material here, this sews to a composite of two different pieces. So this isn't necessarily a bad thing, and this is quite common. So the jumper just tells you that our seam is starting over here, and then it jumps over to this piece here. For the bottom of our chair, we may want to add a hem or additional material to include a drawstring. So if we wanted to do that, we can use the hem tool. The hem tool is almost functionally identical to the seam tool, and they both kind of do the same thing. The only difference is the hem tool is a single-sided operation. So with a seam, we are adding additional material to two sides of the pattern piece, the right and the left-hand side. With hem, we are only adding additional material to one side. So we will start by selecting our edge. Now we can open up the hem tool. And unlike the seam tool, we only have our primary selection here. Most of the tool is exactly the same. We still have our hem properties. This is where we can choose additional material. So whatever hem type you need, you can select that from the list. For my case, I'm going to pick 2-inch hem because I want to create a nice pocket for a drawstring. And now we have our additional 2 inches of material added. If we scroll down, we have access to the notch chain for this particular part. I don't really need notch chain on my hem, so I'm going to turn that off. And now I can apply the exact same hem to this piece over here. For this piece here, this simply sews to another part of quilting that was not included in the model. So this should actually be a seam. However, we don't have the adjacent pattern piece in the model, so I'm just going to treat this as a hem. I'm going to change this to 8 millimeters. So once we have applied all of our patterning information to our chair, I'm actually going to turn the notch chain off for this particular seam here. And we'll leave that alone. So once we've added our seams to our part, we can then move on. We can start adding things like hardware and markings. And there's two different ways that we can do hardware and markings. We can either add hardware and markings in 2D, in our 2D pattern view, or we can add hardware and markings on our 3D model. And this is really a design decision with where it's easiest to add your hardware marking information. If it's easier to place this on the 3D model, then you can do that, and we can map the hardware and markings from 3D to 2D. If it's easier to simply place them on the 2D pattern, then you can do that as well. If you want to just place your hardware and markings on the 2D pattern, we can do that simply by clicking on the pattern piece and creating an in-context sketch. For this piece, we're going to assume that we want to add some decorative buttons, both for decorative looks and to help pull the material in. So buttons are typically point entities. They are an item that is counted in terms of quantity. And for any type of item that is counted as a quantity item, we typically use a point to represent that. Similarly, conversely, if we were to use something like a piece of ribbon or piping or a strip of Velcro, any item that is normally measured in terms of length, we would typically use like a spline or a line to represent that. So because we're going to be adding buttons here, these are items that you would count the quantity, we're going to use a point. And we are simply going to place a point everywhere where we want a button here. So I'm just going to freehand draw these here. We'll add a few and maybe two more down here. And we can dimension these however we want using the existing SOLIDWORKS dimensioning tools. But for the purposes of this demo, I'm just going to freehand draw them. And now that my sketch is done, I'm going to close the sketch. So now we have our sketch here. We have our 8 buttons, and it's in context of the pattern piece. We still need to map this sketch to the pattern piece and effectively register this sketch so it will be included as part of the DXF when we export our DXF pattern. To do this, we just want to make sure the sketch is selected. So we've selected a sketch down there. And now we can open up either our hardware or marking tool. Because we're going to be adding these as buttons, a button is a piece of hardware. It has a physical piece of hardware item that has a cost associated with it. So we're going to use the hardware feature here. Markings effectively does the exact same thing. The only difference is it's typically used for things that don't have a physical piece of hardware. So you would use a marking for something like an annotation text or a fold line or any kind of marking that may help or aid with the assembly of your part. So they both do the exact same thing. They both allow you to transfer sketch information from SOLIDWORKS to your 2D DXF when you export it. So we've opened up the hardware interface here, our sketch, because we selected it before we opened the hardware interface. Our selection has already been pre-populated. If you forgot to select your sketch, then all you will see is your selection. Just simply select your sketch first, and then you'll have access to the rest of the PMP. If your sketch was created in context, then your pattern piece mapping will automatically be selected. If this box is empty, just select the pattern piece that you are wishing to apply your hardware to. Similarly, with edge properties, we have the option to give our sketch a name. So if we wanted to take advantage of Exact Flat's hardware table, we can give our sketch a name, and then that name would appear in the hardware table. So for this sketch, I might just call this decorative buttons. This doesn't have any kind of effect on the functionality of how the marking or hardware is applied. This is only used for information purposes downstream when we create our drawings. As we scroll down, we have our hardware properties. This is where we can change the type of hardware. So if we select hardware, we can pick any of ExactFlat's demo hardware. We're just going to keep our button here, so we will click OK. Just like within the Edge PMP, we can change the default color. So we skipped past this in the seams and hems, but each seam and hem, each piece of hardware and marking will have a color associated with it. And this is simply to help you identify what piece of hardware or marking it is in the pattern environment. So each hardware, each marking, each seam and hem will have a default color assigned to it. However, we can change the default by unchecking Use Default Color and then picking a new color. So if I wanted this to appear in my document as magenta, I can select magenta. And now when I click the OK button here, our sketch is going to turn to a solid color, in this case magenta, and that identifies to us that this sketch has now been successfully mapped to the pattern piece as a hardware sketch. Down here, we have our hem with 2 inches of material to act as a pocket. So down here, we might want to add some information to help us identify where this sews to. So we can do that using a marking sketch. We can do this in either 2D or 3D, whichever is easiest. I've already shown you how to create hardware and markings in 2D. So for this one, I'm going to switch over to my view model. We're going to go back to our 3D model, and I will show you how we can create a hardware marking or hardware sketch in 3D. So because we are in 3D, we want to make sure that we create a 3D sketch. So from our sketch tab over here, instead of just creating a new sketch, we are going to click the down arrow, and we are going to create a new 3D sketch. From here, we can place any kind of point or curve that we want onto our model. The easiest way to create a curve directly on a surface is to use a spline. Click the down arrow and select Spline on Surface, and this will create a new spline on this surface. For this particular piece, we're going to assume that this is a drawstring, so we might want to draw the sewing line for this particular drawstring. So I'm just going to freehand draw a curve on here along the bottom, and we'll assume that this is a the sewing line for a drawstring pocket. So once that spline has been created, we can now close the sketch, and we can see that that curve is very clearly on the surface of the model. You can create this sketch with whatever method is easiest for you. It might be easier to create a plane and intersect it with the surfaces. You might want to simply offset your edges. The method that you use to create your sketch is not important. The only important thing is that we either have some kind of sketch entity or point entities in the sketch, which can then be used to transfer either to the DXF directly or to the pattern piece, and then ultimately to the DXF. So now that we have our sketch created, we're going to make sure our sketch is selected. We can then switch back to the ExactFlat Tools Command Manager. And make sure our sketch is selected and not the entity down here. And now we can apply this as either a hardware or a marking. Last time we did a piece of hardware, this time we're going to do a marking. And they're pretty much exactly the same. We have our sketch selection. The model piece mapping is in most cases automatically determined in 2D view. However, in 3D view, you always need to pick your model piece mapping. So this is just the pattern piece that we want to map the sketch onto. So we will pick our inside left piece here. And then just like with hardware, we can give this a name if we want. And if we scroll down, we have our marking properties. So we're going to select marking, and we're just going to pick our fold line here. We'll keep it at fold line, but we can pick whichever marking type we want. In most cases, the marking type that you select is, again, just for documentation purposes in the drawing. Your choice here is not going to affect your DXF or the function of the tool. in all cases, we are still mapping this sketch to the 2D pattern piece, which will then be exported to the DXF. So this is just for information purposes only. So pick whichever one best describes what you are doing. And when we look at the database manager tomorrow, I will show you how you can create your own custom marking types. And not only that, I'll show you how to create your own custom hardware types, your own custom hem and seam types. So we will pick fold lines, and we will click OK, and we will click OK to close the PMP, and very quickly this sketch has now been mapped to our 2D pattern piece. So if we go to View Patterns here, we can now see our sketch down here has been mapped to our pattern piece. Now that our hardware and markings have been created, the last thing we can do is add a grain line to our pattern pieces. So it's very important that we make sure our pattern is finished and complete before we add the grain line information. It is very strongly recommended that you do not move your pattern pieces or add any new hardware or markings or use a flattener or make any kind of change to your document once the grain line feature has been added. If you've added your grain line feature and you realize that you do need to make a change, before you make your change, you need to remove all grain lines from the document. Otherwise, you will experience unexpected results and SOLIDWORKS will probably crash. It's also recommended at this point to save your document too. So just go to File, Save As, and save your part as a unique file name. So I'm just going to use the default name here and just give it a new name here. So save often, and that will save you the need to redo all of your flattening operations. So now that we're ready to add our grain lines, we can go ahead and open up the grain line PMP. And this tool allows us to apply a grain line to our pattern pieces for use in nesting. So depending on the needs of your pattern, you may have a stripe or a plaid on your pattern piece. You may not have any kind of printed information on your pattern piece, or the material may have a very defined weave that your pattern piece needs to be aligned to. So we can use the grain line to represent how your the orientation of your pattern piece on the marker itself. So to use this tool, we first select the pattern piece that we want to apply a grain line to, and then we have to choose, we can pick either vertices on the part, or we can use an actual sketch to represent the grain line information. So for this part here, we're going to say that we want our part aligned to this edge right here. So over here in selections, I can now pick vertices. So I'll pick that vertex right there, and I'll pick that vertex right there, and that's going to create a grain line between those two vertices. So if I close the tool, we can now see our grain line preview has appeared, and that's telling me that I have a grain line on this pattern piece running in that direction. Down here, I may want the grain running vertical, so I can do that again using vertices. I will open up the grain line tool, piece selection, I will select this piece, and now for my selections, I will pick that vertex and that vertex right there. And when I close the piece, I now have my grain line running vertical. If I want to assign the same grain line to multiple pattern pieces, I can do that. And the easiest way to do that is simply to create a sketch and use a line segment to represent your grain line. So to do that, just create a sketch. I'm going to use my front plane here. I'm going to create a new sketch on my front plane, and let's say that I want my grain line to run at an angle on these pieces here. I can create a single line segment at whatever angle I want, and I can use this line segment to act as my grain line. So now I will open up my grain line tool. For my piece selections, I will select the remainder of the pattern pieces here. And now for my selection, we don't want to select the sketch itself, we want to select the line segment on the sketch. So right click on the sketch, go to select Other, and then make sure you're picking the line segment on your sketch. Once that's done, ExactFlat will project that sketch onto the pattern pieces and assign that as the grain line for all our pattern pieces.